Great pleasure for me to invite Professor T.R. Ramdas to give a first talk in this symposium. I have known Professor Ramdas from, I don't remember, but when did you join TFR?
77.
Okay, so I knew him from 1977 when he joined TFR as a field student. Though I used to talk with, I suppose, students of mathematics. And eventually he shifted to mathematics and did his PhD under guidance of Professor M.S. Narasimhan. He was there for quite some time, and we used to have a chat. Our famous thing is to have a tea time, chat, and whatnot. Then he moved to ICTP, International Center for Theoretical Physics, Trieste, Italy. I don't remember when, how long he was there, but he eventually shifted to Chennai Mathematical Institute, and he is currently professor there. And he has received the most prestigious award, Chantiswara Bhatnagar Award in 1998 for his work in differential geometry. So I request Professor T. Ramdas to give you the
Hello, I hope everyone can hear me. It's a great honor to be asked to speak at this Shreeram Abhyankar birthday symposium. I saw him many times in TIFR, very serious and presence that we all looked up to because of his achievements and his high mathematical viewpoint. And as I said, it's a great honor to be speaking in his birthday symposium. And I thank the organizers for the invitation. I want to talk about things which are more to do with differential geometry. And so the motivation itself is somewhat strange, and I don't think I will, it's hardly relevant here. And in fact, I think, so that, and actually whatever work I have done will come right at the end, if at all. But that will not be enough. I hope what the introductory part will be of interest to the audience, because it describes some very beautiful geometry. So let me start. So here is the unfortunately, my screen is not loading. There is a okay. Now you see it. So I will start with a toy example, and then I will talk about the generalities which will concern the action of n copies of the circle group on a compact symplectic manifold of dimension twice n. So n is some integer, and I have a compact symplectic manifold. I don't think it's relevant. No, of course it's relevant, but for the purpose, I don't think it's necessary to know just what symplectic manifold means. Just treat it as a black box. So you have a manifold, and you have an action of S1 to the power of n, where S1 is a circle group. And under mild conditions, there is a corresponding map given from the symplectic manifold to Rn, where n is the same n. And you can ask, what is the image of this map? And it's one of the fundamental theorems of the field that if you take the fixed point for the action and look at the image under the moment map. So you get a certain number of points in Rn, in fact, a finite number of points in Rn. And if you take the convex hull of those, you get a polytope, and it's a so-called convexity theorem that the image is this polytope. And what is of interest to us will be the question of what is the push forward of the measure, the so-called Liouville measure on X under this man, under the moment map. And it is a very famous and celebrated theorem of Toystomat-Heckman that, in fact, the image is just the Lebesgue measure on Rn restricted to this polytope. So I have written that as Lebesgue times the indicator function of the polytope. So this will be the second part of the talk. I mean, describing these circle of ideas at length. Then I will say which is exactly the symplectic manifold that we are concerned with. That is the following. Take a compact surface of genus G. G is, for various reasons, you should take genus G at least equal to 2. And all compact surfaces of genus are basically classified by the genus. So any two are diffeomorphic. So just fix one of them of genus G. Take the fundamental group of the surface and look at the space of representations of this fundamental group into the group of 2 by 2 unitary matrices with determinant 1, that is SU2. And you go modulo a natural equivalence here, and that's called the moduli space of representations of pi1 of the surface into SU2. And it turns out that this is a even dimensional manifold of dimension 6 times G minus 1. And this is the symplectic manifold of interest. So as I said, I have not told you what a symplectic manifold is, but believe me, this is one. So now I have to look for an action of S1, the unit, remember S1 is the unit circle group. And I must take n copies of this, where n is half the dimension of the symplectic manifold curly M. And in this case, the dimension of the symplectic manifold is 6 times G minus 1. So I must take 3 times G minus 1 copies of the unit circle. And I must look for an action of this product group on M. And it turns out that the so-called Pan's decomposition of the surface, remember we start with the genus G surface, and any Pan's decomposition of the surface gives such an action. And for that, you need a complex structure on your surface. I just said a surface, a C infinity surface. That is why it's just classified by the genus. If you put a complex structure on your surface so that it becomes a compact Riemann surface, then the moduli space acquires a complex structure in turn. And in this avatar, it is the Narsman-Sheshadri theorem that tells you that this is the moduli space of holomorphic vector bundles. So, but I don't have to. It is true that the moduli space is the space of structures. No, that would be the Teichmuller space. So I think you are. I think no. So I think you are confused because of the strange coincidence that this is also 3 times G minus 1. So this is quite distinct from the Teichmuller space. This is the mod E. This is not the Teichmuller space. I will explain this later. Yeah. So thanks for the question. I think people who have encountered the Teichmuller space would legitimately be confused. This is just the moduli space of representations. So in any case, this is the moduli space of representations is a symplectic manifold. If you choose a Pan's decomposition of the surface, which I will explain, remember, I'm still at the outline stage. then you have a symplectic action of this product group, and there is a corresponding moment map. And in fact, I will only describe the moment map. In fact, describing the action itself is non-trivial, and I will not explain it, nor will I have need to do it. Now, by the general theory that I explained before, the image is a convex polytope, and then what I'm interested is integrating various quantities on M with respect to the symplectic volume, which, using the theorem that I mentioned about the push forward of the Liouville measure, amounts to integrating over the convex polytope. Okay. So section 4 is devoted to actually explaining what the what does one mean by the Pan's decomposition, and associated to the Pan's decomposition is a trivalent graph. In this case, it's called a Trinian graph, and associated to that is purely in terms of the graph, there is a Trinian polytope, and in fact, the image of the moment map is this Trinian polytope. So this will be explained in section 4. Then, if we still have time, and if there is, well, if the audience has stamina, I will quickly talk about my own work. I don't think I'll have time to just say that, except very briefly. The motivation is that I want an efficient way of integrating over this polytope, and there is a neat little identity which involves some small bit of Fourier analysis, which, strangely enough, I discovered by something called, it's motivated by something called the Berlin algebra, which comes from algebraic geometry. And the connection to algebraic geometry is via the theorem of Nelson-Sheshavari. So, as I said, if we ever get to that, section 5, to the extent that I have time, I will explain as much of this as I can. But it's really much more, I think, what comes before is of much more general interest. And if there are students, I think the takeaway should be for them to understand the theorem of Doystomat-Heckman about the image of the moment map and the image of the push forward of the Liouville measure, because that is a really fantastic theorem, and it has enlarged substantially the number of integrals that we can do exactly. In mathematics, an integral that can be written down exactly is a very, very precious thing. And the Doystomat-Heckman theorem, which was discovered just a few decades ago, has resulted in our ability to evaluate many integrals. And in fact, it explains many computations that go back to Harishchandra. Okay, so having talked about the outline, let me actually. It's a finite trivalent graph and connected. Those are the ones that I'm interested in. Okay, so let us talk about a toy example where much of, at least, yeah. So imagine that you have a sphere of radius 1, a standard 2 sphere in R3. So you have coordinates x, y, and z, and the radius of the sphere is 1. And so the sphere consists of points in R3 such that x squared plus y squared plus z squared equal to 1. And imagine so in this picture, the north pole is at the top of the sphere, the south pole is at the bottom of the sphere. And you should imagine that this circle is just a sort of top-down view of the sphere. And on the right, I have taken the z-axis and displaced it to the right of the sphere. And so now take 2 points on the z-axis, z and z plus del z, and look at the area of the sphere between these two latitudes. Okay. And it's a simple computation that the area is actually 2 pi times delta z. So in other words, the area of the between, and by the way, so in the picture I have taken infinitesimals, but this is actually an exact computation. If you take two values of z, look at the area between those two latitudes, the area of that slice of the sphere is exactly the difference in the values of z, of the latitudes. So this is a small computation that you can do. And this is really an example of the Doiströmer-Heckmann phenomenon, because the two-sphere is in a natural way compact symplectic manifold of dimension 2. So I must look for an action of just one copy of the unit circle on the two-sphere. And the relevant action here is just rotations around the z-axis. So if I can rotate around the z-axis by any angle between 0 to 2 pi, that's an action of the unit circle. And this preserves area. And in fact, preserving area is the same thing in this case as preserving the symplectic form. So this is a symplectic action. And it turns out that the corresponding moment map is just the map from S2 to the real line, which takes a point on S2 and maps it to the Z coordinate. And so straight away, so what are the fixed points for the Z action? Well, the rotations around the Z axis, there are two fixed points, the North Pole and the South Pole. The North Pole projects to Z equal to 1. The South Pole projects to Z equal to -1. And the image is just the convex hull of these 2 points, namely the interval -1 plus 1. So this is the first part of the theorem that I mentioned, namely the image under the moment map is the convex hull of the images of the fixed points of the group action. Then what is the image? In this case, the Liouville volume element is just the area volume element of the sphere. So if I take the fact that the push forward of the Liouville volume element is as the Lebesgue measure times the indicator function of the polytope, is just a statement that the area between two latitudes is given by the difference of the latitudes, the difference of the z values. Okay, so this is the toy example which perfectly illustrates both the convexity statement, namely, let me repeat, well, let me not repeat because I'm going to do that now in the next section. Okay, so here is a five-minute introduction to Doiströmer-Heckmann. So all these concepts have their origins in physics: symplectic manifolds, symplectic actions, moment maps. So what is the origin in physics? The origin in physics of the notion of a symplectic manifold is that of a phase space. So if you have a number of particles, their positions and momenta constitute the phase space of the system. Of course, these are typically not compact, but it turns out that there are generalizations of this where you cannot divide a point in space into a position and momentum, but which is of both physics and mathematical interest. And those are the compact symplectic manifold that I'm talking about. Symplectic actions correspond to symmetries. For example, if I have particles in R3, then the group of translations preserves everything, acts as symmetries or rotations. And the moment maps are just the momenta or linear or angular momenta. So for example, the group of rotations is SO3. The Lie group is R3. And the moment map is into the Lie algebra. Sorry, the Lie algebra is R3. So the moment maps go into the Lie algebra. And so in this case, linear momentum and angular momentum. Okay. Actually, it should be the dual of the Lie algebra if you want to be strict. So a symplectic manifold is a manifold together with a symplectic form. It's a two form, and beyond that I will not say anything. It's a non-degenerate closed two form. So if you don't know what that means, just take that as a black box. It is a fact that the dimension of a symplectic manifold is even. So I'm calling it twice n. So that and any function on a symplectic manifold in a natural way defines a vector field, and this sets up more or less a bijection between functions and a certain class of vector fields called Hamiltonian vector fields, which are essentially up to some small topological correction, vector fields preserving the symplectic form. So, so the general setup under which the Deutsch-Lemma-Tekman and convexity theorems hold is when I have a compact Lie group, I should have said compact there, acting on a symplectic manifold, preserving omega, and such an action is called a symplectic action. By the way, at some point I should stop and ask for questions because I'm not working on the board and I'm working with a pre-prepared presentation. I am talking too fast. So, so let me, at this point, stop and ask, first of all, the audience in the room, are there questions? Professor Kulkarni already connected. Yeah, so the formalism of moment maps only sees the Lie algebra, so we can assume it's connected.
Net groups are out.
Yeah, for finite groups, the formalism, yeah, doesn't. Are there other questions? So, okay. So I'm, yeah.
Hello. Hello.
Yeah, I think there is a question.
So in case of the circle or the sphere that was rotating, am I audible?
Just barely. Can you turn up the volume? Just wait until we see if we can turn up the volume.
Hello?
Yeah, this is much better. Yeah, go on.
Okay. So in case of the sphere that was rotating, I guess it was the sphere that was rotating. So what exactly was the moment map? The
moment map is the Z coordinate. So let me repeat. So the sphere, in this case of the sphere, the symplectic form is essentially the volume form. The group in question is the group of rotations around the Z-axis. So that is just one copy of S1. So the moment map will be to just one copy of R. And that is the map that sends a point of the sphere with coordinates X, Y, Z to the coordinate Z, the value of the Z coordinate.
Okay, thanks.
I mean, this is subject to various normalizations, but up to I think if the radius of the sphere is 1, and if the total volume is taken as 4 pi, this is correct.
Okay.
Yeah. Any other question? Okay. So yeah. So let me go on. So I am now considering that. So this is the situation that we are considering. As I said, this is the most important part that at least the statement, because I'm not saying anything at all about the proof. The statements you should really try to take away because they are of really wide applicability. So you have a compact symplectic manifold of dimension 2n, you have a compact Lie group. Let me just for Lie, just 1 second. You have a compact Lie group acting on X, preserving the symplectic form, and this is called a symplectic action. Yeah. What is the definition? I will say the definition in a minute. Okay. So under mild topological conditions, there exists an associated map, which is from X to the dual of the Lie algebra of G, and it's really important to, in general, to know that at least one more factor. So, I have not defined what is the, I've told you what is the defining property of the moment map, which is the question that Professor Kulkarni asked. I will come to it in a minute, but it's important to already know that there are mild conditions under which the moment map exists. They are algebraic topological. And the map is from X to the dual of the Lie algebra of G. Now note that on both sides of the map, I have an action of the group G, because we started with symplectic map manifold with an action of the group G, and the dual of the Lie algebra has an action of the Lie group G called the co-adjoint action, and the moment map is actually equivariant under these actions. So in other words, if I take a point of X, it will go to mu of X. If I take an element of G, act on X by that element, so I get an element, I get a point Gx. Mu at Gx will be related to mu at X by the co-adjoint action of G on the dual of the Lie algebra. Okay. Now, Professor Kulkarni asked me what is the defining property of the moment map. Can I come to that question after I sort of give the punchline of this section, which is in the very important special case when the group consists of the product of S1 n times. In other words, it's a compact abelian group, n-dimensional abelian group, which is given by taking just n copies of the unit circle, so that then the Lie algebra of G can be naturally identified with Rn, and therefore the dual also with Rn. So we have a map from X to Rn. So in this case, there is no, the co-adjoint action is trivial because the group is abelian. There's no action, group action, but anyway, there is a map from X to Rn. And the convexity theorem says that the image of mu is a polytope. In fact, you take the fixed points of the group action on X, which are finite, take the image of those points in Rn, and take the convex hull of those points, and the image of mu is exactly this convex hull. So this is a polytope because it's a convex hull of a finitely many points. And so this is the convexity theorem. I think in this case, the convexity theorem goes back to, I think, Delzant, but various generalizations were proved, I think, Attia, and then Gilman and Sternberg through generalizations of this. And the Doistomat-Heckman theorem is that up to normalization, the push forward of the Liouville measure on omega is a Lebesgue measure on Rn restricted to this polytope. So there are two terms I should explain here. What is a Liouville measure on omega? So this is any symplectic manifold has a natural volume element that comes from the symplectic form. In fact, in Hamiltonian mechanics, one of the things you learn is that this volume element is preserved by Hamiltonian flows. And what is the push forward of a measure? Well, in simple terms, what this means is that if I take any function of the of the moment map variables of the n variables in Rn, and if I put them back to the manifold X and integrate with respect to the Liouville measure, that's the same as integrating on the polytope the same function. So that's what push forward means. And so the theorem of Dijkstraat-Heckman is therefore quite powerful. It says the push forward of the Liouville measure on omega by the moment map is the Lebesgue measure on Rn restricted to the polytope. Now, before I ask for questions, let me address Professor Kulkarni's question. So, what is the connection between the moment map and the group action? So, let us assume that the group in question is just one copy of S1. So, then the moment map is into R. So, what is the connection between this R-valued function and the action of S1? The connection is the following. As I told you, on a symplectic manifold, any function defines a corresponding vector field called the Hamiltonian vector field. And the connection between the action of the group and the moment map, in this case, is that if you take the moment map, take the Hamiltonian vector field corresponding to the moment map, that is the influential vector field corresponding to the action of S1. Now, if you want to generalize this to arbitrary group, then for various bookkeeping purposes, you must think of the moment map as going into the dual of the Lie algebra, and it's essentially the same definition works. Are there any questions from the online audience? Okay, so let me repeat. When I have a symplectic action of the n-fold product of S1 on a 2n-dimensional compact symplectic manifold, there is a corresponding moment map which is into Rn. The image is the convex hull of the images of the fixed points of the group action under the moment map. The push forward of the Liouville measure on the symplectic manifold is just the Lebesgue measure on Rn restricted to the polytope. Okay. So now let us consider the situation at hand. So I promised that I will exhibit a certain symplectic manifold that comes from essentially the differential topology, in fact, just the topology of compact surfaces. So compact oriented surfaces. So a compact oriented surface up to diffeomorphism or homeomorphism is basically classified by giving its genus, which is, if you draw a picture, it's just the number of holes. So what you see is genus 4 surface that I've drawn. Now, take the fundamental group of this surface, and it is a fact that if you choose a circle of alpha loops, and to define a fundamental group, you first must fix a base point, and then you must consider loops, closed loops, beginning and ending there, and then you must define the fundamental group. So it is a fact that if you have a compact genus G surface, if you choose a system of so-called alpha loops and beta loops, which I will illustrate below, then the fundamental group is the group generated by the G alpha loops and the G beta loops subject to one condition, namely this product must be the identity. So if you take alpha 1, beta 1, alpha inverse, beta inverse, alpha 2, beta 2, alpha 2 inverse, beta 2, and take the product up to G, then that must be the identity. So it is a free group on 2G generators subject to one relation. Okay. And for example, if you take a genus 2 surface, I've taken a genus 2 surface here. I've fixed this as a base point, and I have shown 2 loops that start, and each of which starts and ends there. Namely, the first loop is this alpha loop, and the second loop is this beta loop. And similarly, there'll be a alpha 2 loop and a beta 2 loop, like that. And these 4 loops will generate the fundamental group subject to one relation. So now, what would be a representation of pi1 of sigma into SU2? So forget the equivalence, because that is important, because the moduli space is representations up to equivalence. So that is what I have expressed in this sort of set theoretic fraction that you see here. There is a set here, and there is an equivalence relation here. But let's forget about the equivalence relation. So let's just look at this so-called, let's call it the numerator of this, namely this, and try to understand that. So that is just the space of representations of pi1 into SU2. So remember, pi1 is this free group generated by these symbols or these paths. Giving a representation means that you have to give for every element of pi1 as sigma an element of SU2 in such a way that relations in pi1 of sigma carry over to under this representation. So if you think about it for a few minutes, you will see that giving a representation is the same thing as giving 2G elements of SU2 which satisfy this condition. So that is the numerator here. And what is the equivalence? Well, if you take 2G elements AI, BI, and if you take some other 2G elements like that, and they are equivalent if they are related by conjugation by a fixed common element of SU2. And if you do some dimension counting, well, each element of SU2 has dimension 3. There are 2G elements, so that would give you 6G. But I must consider, one second, that they satisfy one condition, that takes away 3. And this quotienting by this takes away another 3. So I get 3 into 2G minus 3 minus 3, which is 6 times G minus 1. There is a question online. I thought I heard some question. No? No. Okay. Very good. So at least, even though I have not given you a symplectic structure on this manifold, well, I haven't even shown you that this is a manifold, but that you can kind of imagine is the case because SU2 is a manifold, and putting one constraint on that of codimension 3, that's given by this condition. So you can imagine that this is a manifold, and then I'm going by a quotient relation. So if you're lucky, this would be a manifold. Actually, that's not true. I mean, there are small mild singularities which we will ignore. Okay. So it's a manifold except for some singularities, and it has dimension which is even, and it's not that difficult, but it will take some time to put a symplectic structure on this. Okay. So now, there is a symplectic structure. So now I have to, So now I have to, going by logically, the next thing to do would be to exhibit a symplectic action of S1 to the power of n, which is n is 3 times G minus 1, and write down the corresponding moment map, which should be to Rn. I'm not going to do that. I'm going to give you a class of functions into R. Then I'm going to take n of these functions and declare that these are the moment maps for an action. Okay. So to start with, let me give you one function on this space. So far, we don't know any natural function. So let me give you at least one. So imagine that you are given some loop L on your surface. So remember, our surface in this case is this. I start with some loop. It could be one of these alpha or beta, okay? But it need not be. And supposing I'm given a loop and a representation, then we can evaluate the representation on the class of the loop. So you remember, each loop on the surface gives you an element of pi1 of the fundamental loop. So I can evaluate the representation on that element of pi1. Then I'll get an element of SU2. And if you take its trace, if you take any element of SU2, its trace belongs to it's a real and belongs to the interval minus
recording in progress.
Hello? Is there a question? Okay. So any element, any real number in the interval minus 2 can be written with a little bit of ambiguity, which I'm going to ignore, as 2 cos, twice cos pi times a real number which runs between 0 and 1. And that is the function that I'm going to associate to the loop. So let me repeat. So I'm fixing the loop L, and I must give a function on the space of representations. Namely, take any representation, evaluate the representation on the fundamental element of the fundamental class given by this loop, take the trace of that, write it as cos twice cos times pi times real number in the interval 0, 1, and take that real number. That is the function that I associate to one loop. So you may not know why I'm doing this, and I certainly haven't motivated it, so it is not your fault, but I hope you at least see that associated to every loop, there is a more or less natural real valued function on the space of representations, which takes, because of the construction, values in the interval 0, 1. Now, it is also clear that if I take 2 homotopic loops, they are going to give the same element of the fundamental loop, so they give the same function. And contractible loops will give the constant function 0, because the contractible loop, if I evaluate it on any representation, it will give the identity 2 by 2 matrix. Its trace is 2, and that corresponds to t equal to 0. So we must, to find an interesting families of functions. Remember, I want to get 3 times g minus 1 functions. So I must find non-homotopic, non-intersecting functions. And somewhat magically, these correspond to boundary circles of what are called Pan's decomposition. So I will not define for you what is a Pan's decomposition, but it is a fact that if I have any finite family of non-intersecting and non-homotopic, mutually non-homotopic loops on a surface, first of all, you cannot find infinitely many of them. And in fact, you can only find 3 times g minus 1 such things. And any finite family can be extended to a maximal family consisting of 3 times g minus 1. And if you do that, they will define what's called a Pan's decomposition, which is a figure like that you see here. I seem to have stopped broadcasting. There is a glitch here, so we will figure this out in a minute.
Hello?
Yeah.
So the Pan's decomposition you're talking about, is it just for the surface case, or like it can be in any even dimension, the Pan's decomposition?
Wait, no. So see, remember that just give us a few minutes because there is a glitch with the broadcast of my screen until that. While they are fixing the screen, perhaps you can ask your question. Hello?
Yeah, so the PANS decomposition you talked about, it's in any even dimension, is it? Or
No. See, remember, the surface is not the symplectic manifold that we are interested in. You take the surface and and the only relevant thing about the surface is the genus. Even though I draw these pictures, it's relevant. The picture is relevant, but the moment I fix G, I have a given manifold of dimension 6G minus 1, which is the space of equivalence classes of representations of pi1 of the surface into SU2. That is the symplectic manifold. So the surface is referenced only to get hold of the symplectic manifold. And the PANS decomposition of the surface leads to an action of the N torus on this symplectic manifold. Is that clear? Yes. So I'm not talking about PANS decomposition of the symplectic manifold. The PANS decomposition of, so the surface, you start with the surface of genus G, that leads you to the consideration of the space of representations of the fundamental group of that surface into SU2. That is the symplectic manifold of interest. Now, to give an action of S1 to the power 3 thrice G minus 1, I go back to the surface and take a PANS decomposition of that. So there is a toing and froing that I'm doing. Does that help?
Yes.
Hello?
Yes.
Yep. So, yeah, here you see one particular PANS decomposition of my genus 4 surface. So, what is a PANS decomposition is a decomposition into what are called pairs of PANS. Imagine that you have a pair of PANS. Remember, so if you just take a pair of PANS and hold it up, there are 3 boundaries. So it's a kind of cloth stitched in a certain way. There are 3 boundary circles, namely the one around the waist and the one around at the end of the 2 legs. So this is called a pair of. I mean, sorry for the crazy English. So this is called a pair of PANS. A pair of PANS is just one of these. Okay. The French call it a trinium. So what you have here is I have taken this genus 4 surface and I have divided it up into 6 pairs of PANS. So one is this one pair of PANS, and another one. This is the one that's clearly a pair of PANS. See, just this pair. Like that. I'm sorry, I cannot draw in a hurry. But here is a pair of PANS. Here's another pair of PANS. Here's another pair of PANS. So there are 6 pairs of PANS here. So it's important to note that there is no unique PANS decomposition of a surface. There are, in fact, the space of PANS decomposition is a great interest manifold. 9 boundary circles here, which is not coincidentally, which is the same as 3 times G minus 1. So, fact, any Pan's decomposition has twice G minus 1 Pan's and gives 3 times G minus 1 non-homotopic and non-trivial loops L1 to L3, L 3 times G minus 1. And this corresponds to the moment map for S1 cross S1 cross S1, 3 times G minus 1 times on M. So there is no hope that, so this is in some sense the deepest part of this work, which is due to Goldman. In sort of great generalities, he described functions on the so-called character varieties, which are representation spaces of fundamental groups in various groups, and corresponding functions. And he also described the corresponding actions. Okay? So now comes the question, how does one describe the image polytope? So I'm going now at somewhat great speed. I start with the surface of genus G. I take a Pan's decomposition. That gives you, the boundary circles give you 3 times G minus 1 functions. And I have declared that these functions, which are each of these is real value, I've declared that these 3G minus 1 functions, which give a map from the moduli space of representations into R to the 3G minus 1, correspond to an action of S1 cross S1 cross S1 3 times G minus 1 times that I've just declared to you. You have to take it on faith. And so now if you go back to the convexity theorem, it tells you that the image is convex polytope. And you can ask, how do I describe this convex polytope? And this has a nice description. For that, you have to bring in another object called the Trinian graph that's associated to the Pan's decomposition. So here I have drawn for you the Trinian graph, which is a trivalent graph associated to this Pan's decomposition. The vertices of the graph correspond to pairs of Pans in the decomposition. So there are 6 pairs of Pans in my decomposition. They are given by this violet points. And so they correspond to these vertices 1, 2, 3, 4, 5, 6. And the edges correspond to common boundary circles. And you will see there are 9 boundary circles. Here is one. Here is one. I hope I get this right. Here is one, here is one, here is one. There are 9 boundary circles, and the edges correspond to these boundary circles. And the Trinian graph actually gives you a description of the corresponding polytope. So let me let me do that in some generality. Supposing I am given a trivalent graph tau with n edges, define the corresponding polytope in R to the n, except that you think of R to the n as each element, each coordinate as labeling one of the edges of the Trinian graph. And what is the polytope? It's given by these constraints on the coordinates. Each coordinate Ti runs between 0 and 1. And for every vertex in the graph, if 1, 2, 3 are the edges meeting there, then the corresponding variables T1, T2, T3 must add up to 2, and they must satisfy this triangle inequality. Okay. So this must hold for every vertex. So of course, you know, for the general vertex, I mean, I can't keep labeling everything T1, T2, T3. So remember, there are n real, the Rn has these n coordinates, but each coordinate is attached to one edge of the Trinian graph. So what are the constraints on these coordinates that describe the polytope? One constraint is very easy. the polytope must be contained in the hypercube in R to the n, where each coordinate runs between 0 and 1. But the non-trivial constraints correspond to vertices of the Clinian graph, namely the 3 for each vertex. The variables associated to the edges that meet there must add up to less than or equal to 2, and they must satisfy this triangle inequality. Now, geometrically, what this means is that pi times T1, pi times T2, and pi times T3 correspond to the sides of a spherical triangle drawn on a sphere of radius 1.
Indresh?
And here is a picture of the constraints on T1, T2, T3. This is just a slice of the polytope, meaning the polytope is in n dimensions, but I can see, supposing n was 3, what would it be? And this is the polytope. Okay, now I have 10 minutes. So, so the next step is to handle the polytope to understand. So I'm now going to abandon the general polytope and spend the rest of the lecture just trying to understand the simplest polytope, which is this 3-dimensional polytope. So the 3-dimensional polytope P3, which I will soon begin to just call it P. So you shouldn't confuse that with the general polytope, n-dimensional polytope. Okay. So this consists of points in R3 satisfying these conditions. Okay, so are there questions now? Because as I said, now I'm going to kind of, it will look as if I'm going to an entirely different universe because to actually efficiently integrate over polytope, as I said, involves a little bit of Fourier analysis and perhaps there is information overload already here. So I just, so let me just, because we started a little late, I don't think, see let me just say what, in words, what the key thing is. The key observation is that if I take this polytope and fix the variable T3, so in other words, take a slice like this, okay, then it will look like, so if I fix the variable T3, then I'll get the slice will be a rectangle like this with corners at these 4 points. And so here, so this is a variable rectangle parameterized by T3. So now take this rectangle, take the indicator function of that rectangle, and think of that as a kernel of a linear map from L2 of this R to L2 of this R. So in other words, you look at the convolution by the kernel, which is the indicator function of this rectangle. So these are integral operators. So now for some reason I have replaced T3 by A. So you look at the convolution by the indicator function of this rectangle. So okay. So now I will just say in words. I think there's a glitch here. We are running out of time. I don't want to intrude into the time of the next speaker. So I will just say in words. The key thing is that Okay. So, let me just say in words. So, I want to understand something about this three-dimensional polytope. And if I fix the z variable, which is, sorry, the third variable T3, so which means slicing this three-dimensional polytope by a two-dimensional plane, I get the rectangle whose picture I showed you. So that's a variable rectangle that depends on the T3 coordinate. For each of those values of the T3 coordinate, if I take the indicator function of the rectangle, that gives you an integral operator by thinking of that indicator function as a kernel. So the key computation is that for different values of T3, these integral operators commute. And this is not at all obvious, and this was I was led to this from an entirely different formalism, which comes from algebraic geometry called the Bernoulli algebra. Once you think that this might be true, it is straightforward computations to verify this. Then you simultaneously diagonalize this family of operators. They turn out to be Hilbert-Schmidt, if you know what that means. Then that gives you an Fourier expansion of the indicator function of the three-dimensional polytope, which in turn can be bootstrapped to give a Fourier expression for the n-dimensional polytope, which enables us to do various efficient computations regarding these loop functions, which are, I said, in an efficient way. And I was able to come up with interesting expression and interesting conjectures. So with that, I stopped my presentation. Once again, thanking you everybody for their patient hearing, thanking the organizers for this invitation, thanking you for your patience with the glitches, and hope that so to the students, I encourage them, the takeaway is the convexity theorem and the Deutsch-Stromer theorem, which I have nothing to do with. Yeah, thank you.
Thank the speaker, Ramdas. Anybody has any questions?
Constant had some word on that. I think it's constant, yes, of course, but you know, Gellerman, Sternberg, and Akia are the people who get the convexity theorem. But this the Abelian case goes back to several people.
What is the kind of motivation?
Why am I doing this? That comes from case theory. And see, even though Goldman introduced this a while ago, and people have considered these functions, nobody has thought to ask what is the joint distribution of these functions with respect to the Liouville volume. And in fact, once I have this formalism set up, there are very nice computations you can do. For example, if you take just one loop and take the push forward of the Liouville measure under that one single function, you get a measure on the interval 0, 1, which depends on G. on the zenith. In the limit of large G, this tends to the Weyl measure, twice sine squared, twice sine squared by whatever. You know, the Y, which is the measure on U1 given by, you know, the take an invariant function on SU2, then integrate that, sorry, a class function on SU2, you know, the Weyl integral, you know, Weyl integral formula. So in the limit of large G, this tends to that number. Yeah, there are such things. Quite, okay, thank you.
So I thank the speaker from us, also the chairperson for this talk, Professor Bhatodekar. And now we have 5-minute break, and after that we will start the second talk.
The content of what?
Hello. We shall now be starting the second talk. Second talk is by Professor Ravi Kulkarni, and I request Professor Abhyankar Joshi, who is the head of Department of Mathematics, Savitribai Phule, Pune University, to chair this session. Professor Abhyankar Joshi.
Thank you, sir. It's my privilege to introduce Professor Ravi Kulkarni. Professor Ravi Kulkarni is a very well-known mathematician working in differential geometry. He completed his PhD from Harvard in 1968. He worked with many US universities, starting from Johns Hopkins, Columbia, Indiana, and City University of New York. And he's associated with IIT Bombay and SPPU, Open University. And I do remember that in 2010, we had a conference in honor of Professor Shreeram Abhyankar on his 80th birthday. With this brief introduction to Professor Kulkarni, I request you, sir, to start his lecture. Thank you.
I knew Professor Abhyankar now maybe for 60 years or so. Even before I left for New York, I had heard about him, and I met him just 2 years after I went to Harvard. And our careers have intersected in some intricate ways. So, next one. Yeah, so I should start with some particular reminiscences. Then I'm talking on this famous paper, Historical Ramblings.
Recording in progress.
Algebra. This paper was published in the American Mathematical Monthly. And it kind of gives a review of his work until 1970 or 76, I think. Yeah. And the way he thinks. Yeah, I think it will be a good thing to understand this paper in really some depth. And I requested Professor Katre to arrange some, not just seminars, just 1 hour seminars, but just some 1 week of some people like Sudhir Gorpade, Kapil Paranjpe, Ramanan, and these people will do they probably understand a good part of this paper, and they will be able to say more, and we shall all benefit out of that. We shall get something out of that. So I met Professor Abhyankar in 1964 at Harvard. I just passed my PhD qualifying exam in the summer of 1964. Craig was my officially assigned advisor. Zariski had organized a 1-month summer institute at Woodstock, Massachusetts, on algebraic geometry. I asked Craig whether I could attend it. With his support and encouragement, I attended that institute. And Abhyankar was invited to that institute. It was a 1-month institute. That is where I met him first. Zariski, Tate, Sayre, Bott, Nagata, Abhyankar, Hironaka, Mumford, Matsushima, Cassels. These are some big names in algebraic geometry and number theory. There are still some big names, but they were they all were many of them were there. Zariski was, of course, there. There were some of the stars at that institute. The same year, he also spent a semester at Harvard. And again, I met him. I learned that Zariski was trying to get a regular faculty appointment for Abhyankar at Harvard. Abhyankar was a favorite student of Zariski, as he had solved in 1954 the local uniformization problem for algebraic surfaces over fields of characteristic P. Abhyankar was also very proud of his thesis. I heard the stories about it from him 3-4 times. And I shall try to explain what I understand what this thesis was and its background. Uniformization has at least two very different meanings. One is topological, the other is algebraic geometry. Let me tell you the algebraic geometry as I understand it. For the topological part, I shall come later. If I'm making some errors, I request the experts to correct me in this. Let K be an algebraically closed field of any characteristic, and K a finitely generated field extension of transcendence degree n. Question: does there exist a non-singular projective algebraic variety capital X such that K is isomorphic to the meromorphic function field of M? I think experts may correct me, but probably this is the original problem. Now, of course, you can ask if it exists, is it unique? If not unique, how many? Better can we parameterize this set of N's, and so on. So these are the issues. In case K equals complex numbers and N equals 1, so the transcendence degree is 1. The answer is yes, and that is due to Riemann, not directly that in this form, but in some convoluted way, Riemann had all the ideas there. The proof uses, of course, the transcendental methods, and actually the object that we get finally, it will be a complex projective curve, and that will be an algebraic curve. And that is actually unique, and that is a compact Riemann surface of genus G. When you say surface, that is over the reals. It's two real dimensional, and it's one complex dimensional. And it has no singularities, it's non-singular as an algebraic curve, as well as the manifold, and so on. So a natural question, the final result is algebraic. Can we prove it algebraically? So that the statement is true for K equals any algebraically closed field of any characteristic. For example, algebraic closure of the rationals or algebraic closure of a finite field with P elements. I think the case N equals 1 was probably settled by Noether, but I'm not sure about this. The Max Noether, father of the Emmy Noether. As Abhyankar recalls, his Max Noether's AF plus BG theorem purely in algebraic geometry is equivalent to the Riemann-Roch theorem when K equals C. I think this will be a very good exercise. It's not just an exercise. It's understanding two different viewpoints. And Riemann-Roch theorem is a deep theorem, and how to how this Max Noether theorem translates into Riemann-Roch theorem. The case N equals 2 was extensively studied. Studied by Italian algebraic geometers. Probably over, I think probably over algebraical closed fields of characteristic zero. Brought rigor to their arguments, and n exists, but it is not unique. For instance, if you take two copies of the complex projective line and two-dimensional complex projective space, both have the same meromorphic function field in transcendence degree 2, and no further algebraic extension of that. There is the study then the minimal models problems, that there are at least these two examples for just kxy, and what are some other models which will have the same, and this is just for the transcendence, purely transcendental extension, and some other things. So Abhyankar's thesis was the case n equals 2 for a non-zero characteristic. And at this same, as the title of his paper thesis says, he solved a local problem, stated in the title of his thesis. I think given K, capital K, that is, you have a transcendence degree n extension of little k, and with some algebraic extension after that. This is your data. Now, from that, I think it should be possible to write down some rational functions and other things in n variables, and maybe even polynomials finally, and to say that, so that's where the capital K is the field obtained by the generators over little k. So I think given capital K, it is easy to write down equations for some irreducible projective algebraic variety with function field K. And it's capital K is a field, and this variety is irreducible because it should correspond to the prime ideal and so on. The usual results in algebra. So for n equals 2, Abhyankar solved a local problem, namely he resolved the singularities. So you get some algebraic variety, but it has singularities. And there is some local procedure to resolve the singularities. And that was a brilliant thesis. I think this determined major directions in Abhyankar's subsequent work. And I do not know, he may have done some work on the minimal non-singular models also, like the Zariski. But probably the experts may know whether he accomplished anything in that, or whether it is worthwhile pursuing that direction. I may just mention how Abhyankar's thesis probably helped me personally in my personal life. I don't know the original paper itself, but it helped me in a very indirect way. Zariski used to give many times an undergraduate course, Mathematics 103 it was called, and it was an undergraduate course on projective geometry. I think at that time I also had a course in projective geometry from Professor Reiter. And he was, he taught whatever was in the syllabus, but there were some natural questions about which he was a little hesitant. And that was a very standard course at that time. And this Math 103 is mentioned by Abhyankar also in this paper, as well as he mentions it many times. I felt that Zariski was always rather unusually kind to me, very unusual. For he was a big professor, I was just a starting student. I learned much later that Zariski was the person who was in the selection committee when I applied for admission at Harvard. When I had not yet finished my PA exam. I had not finished the exam. My recommendation letters went there. Zariski was in the admission committee. So he gave me an admission, provided I passed the BA exam. So I had to produce the BA exam certificate from Pune University, and then I would get the admission. It's a very unusual for in the usual circumstances. So I'm not completely sure how it happened, but probably this was the way I have personally benefited from Abhyankar's thesis. I do not know if it was the right direction for me to go to Harvard just after my bachelor's. I had to work very hard. Anyway, I took the chance, and before that, many people in Pune, including my father, were advising me to try for IAS. In my first year, Prof was officially assigned as my advisor. Prof was my group theorist. And then Tate was assigned as my advisor in my second year. It's just a formal assignment, not a serious thing, but I could go and talk with them some mathematics and so on. From the second year, I started attending many seminars. I mused whether I should work for PhD with Zariski or Tate in algebraic geometry or number theory, or go back to India and try for IAS. Sharad Kale, 2 years senior to me and with a similar career, had succeeded in becoming an IAS. During that visit in 1964, Abhyankar was very kind to me. He spent a semester at Harvard. I liked swimming, and I used to go in the pool there, and so did Abhyankar. So many times we used to go to the pool together. In the same year, Professor M.S. Huzurwada from Pune, the statistician you know, and he had won a big prize at that time, some Smith's Prize at Oxford. He came to visit Abhyankar. I think he was also trying to go somewhere in the United States. I think he later went there.
Yes.
No, V.S. was mathematician.
Yes was here.
Yes, was statistics.
Oh, yeah, I should say yes. MS was in the mathematician. And they are both uncles of Jan Narlikar. So Jan Narlikar, I heard about him around the same time. I remember a nice dinner at Abhyankar's house in honor of Professor Huzurwada, and I was also invited. There I met Abhyankar's wife, Yone. Very charming, motherly, very hospitable. I think his wife took extremely good care of him. And he himself said that she should be given perhaps half the credit for all the professional success he had. And similar to Mangala and Jan Narlikar's story. At Harvard, there is a nice system that before embarking on one's PhD thesis, one has to write a minor thesis in 1 month. Only 1 month time was given, and on a subject different from the one intends to write one's thesis. So they thought that I was interested in algebraic geometry, number theory. So they assigned Professor Sternberg, who was a differential geometer, and he gave me a topic. The strictly 1/4 pinched, simply connected, compact Riemannian manifold was homeomorphic to a sphere. This is the theorem. It was a hot topic at that time. I think Sternberg had proved the major theorem in 1962, and I was writing on these papers in 1965. Well, Sternberg liked my exposition. He also tested me orally if I really understood what I wrote. I had simplified the proof and proved some new results. That was my first introduction to Riemann and many contemporary top mathematicians like Milner at that time. In the summer of 1965, I wrote to Abhyankar whether I could informally come to Purdue and get some research grounding in algebraic geometry. But somehow Abhyankar discouraged me. Maybe he thought that I did not have enough background in high school algebra, and I was just parroting this or that homology and cohomology. He used to say that openly in our conversations. Anyway, somehow, I don't know why he discouraged me to come to Purdue. But anyway, in those days at Harvard, the hero of algebraic geometers and number theorists was Grothendieck. You may guess the atmosphere from what Abhyankar writes about his distaste for university algebra in his historical ramblings. I was not at all sure whether I could write a reasonably good thesis in Prof. style. So I turned to Professor Sternberg and asked him whether I could work with him. He had liked my minor thesis, but I had not taken any courses, regular courses in differential geometry. Still, he agreed, and Tate was a bit annoyed because Tate thought I would be working with him. The risk was rather old at that time. But such is the integrity of places like Harvard that Tate did not mind. And finally, at my thesis defense, Viva, Brower, Mumford, Tate, Gleason, and of course Mazur was turning from topology to number theory at that time. And Sternberg and Bott, they all attended my PhD Viva. Then for about 10 years, until 1976, I lost contact with Abhyankar. In 1973, his student Mo and I spent a year in Princeton. I tried to learn some Abhyankar type algebraic geometry from Mo. I was not successful. After I joined University of Indiana at Bloomington in 1976, I went to see Abhyankar at his home a few times at Purdue University at Indianapolis. It was about 50 miles away from my place. We talked about doing mathematics, doing something for mathematics in India. And Bhaskaracharya Pratishthan idea came at that time, in 1976. I fully supported him, but Abhyankar, but besides that, he had no actual talk about mathematics. This is the thing. He even did not come to any of my math talks at the topology geometry seminars at Purdue. I had to go to his house after my talks were over to see it. There are some similarities in our careers that both Zariski and Sternberg had good personal contacts at Johns Hopkins. And our first jobs were at Johns Hopkins. And both Abhyankar and I had the first non-tenured job. It was always, first job was always non-tenured. And then we had both tenured jobs, second tenure, non-tenured jobs. I had this non-tenured job at Columbia University, and I do not know whether he had a tenure at Cornell or not, but his second job was at Cornell University. And then we both had tenured jobs at Indiana State's land grant university. Indiana State has two major universities. This arts kind of university is the University of Indiana at Bloomington, and science or engineering kind of land grant school was at Purdue University at Indianapolis. We met a few times, but my memory of him was the usual shop talk about mathematicians. He used to drop in names like Grothendieck, Sayre, Zariski, and praise or criticize them. Once Harishchandra also mentioned the same to me about Abhyankar. But he doesn't talk mathematics, he talks about mathematicians and how he was friends with Sayre. I think he didn't like, perhaps Grothendieck, and he did not talk very much, but Sayre and he used to talk. But somehow there was no mathematical interaction among us. In fact, I do not remember a single fact in mathematics that I learned from him in conversation. I feel that had he been more communicative, I could have loved to write some joint papers with him, done work with him, and he could have accomplished a lot more for mathematics in India, which was his cherished dream, as it is a dream for many of us. Later at CUNY, I'm giving a rather long talk. Perhaps some of the teachers do not know, some of the stories you do not know. There was a vacancy of distinguished professor level at City University of New York. I do not know exactly what happened, but the chairman of the CUNY math department asked me to write a professional report on Abhyankar. Now, I did not know all his works, and I was not an expert there. So I wrote to Abhyankar and requested him to give a summary of his important results. He did not write anything to me, but sent me 2 large envelopes full of his papers. Now you read these papers and whatever you want to report on that. Okay. He and his wife came to CUNY. I took them for lunch. He gave a talk. But somehow CUNY did not make him an offer. Somehow people mumbled that his teaching style was not suitable for a place like New York. It is a very crowded place, and anyway, and I did not receive any communication from him after he left New York. Not that, okay, you reported on my work, good. Nothing. Well, I don't know whatever happened between him and Bhaskaracharya Pratishthan and Pune University and TIFR, many of you know better. Then I came back to India in 2001 to Harishchandra Research Institute. I often invited him. What annoyed me was, we would have, of course, given him always special treatment. He was a great mathematician. But he demanded a special treatment. His travel expenses were always very high. I don't know whether he traveled by first class or something. And TIFR would not sanction them. And I had to sign up on those papers from Harishchandra Research Institute. And the auditor hopefully did not raise any objections to whatever I did. That brings me to question about Abhyankar as a person. Professor C.S. Inamdar, who was the custodian here, had called Abhyankar, me, and some others for a dinner meeting at his house. I think you were not there. I was amazed that Abhyankar was personally a visit to Professor Inamdar. Just amazed. That is the unique experience in my professional life. Again at IIT Bombay, Sudhir Godpure had invited him. He was supposed to give a math lecture. It contained no mathematics. And it was highly unprofessional. Again, an unusual experience in my professional career. Historically, such problems are there for many great scientists. We know Newton and Leibniz feud, Bernoulli brothers feud, and so on. And there are also many contemporary analogs of this. I feel that the scientific community should come to some consensus about handling such issues of our heroes, just for the benefit of our noble profession. It's not good for mathematics to hear about such stories. At least we should start talking about these issues, and we should effectively convey the message that in final analysis, the message is important, not the messengers. Okay, now after this long introduction, which I will not have given anywhere else, let me start with the. So I give you a topological background of of this paper. So let me start with complete generality that categories of mathematical thought, these are number and space. And these map neatly onto categories of physics thought, time and space. Number maps onto time and space is space. But what do these mean? The space category in physics, the idea of space is just the Euclidean 3 space. In math, the ideas of a topological space, measure space, contact manifolds, etc. These are ideas of in math. Okay, and now the main starting example of a space in mathematics is the real line. I always like to distinguish between the real line and real numbers. Real line is the line that any child draws when he has a pencil and a paper. Mathematically, it is a complete ordered set without minimum or maximum, and that contains a countable tensor subset. This is the understanding of dedicate. And the really major result, the real line is unique. In what sense? Up to order preserving isomorphism. I think when we discuss these topics in the master's level, we should really distinguish between real line and real numbers and present the topic that way. I think I don't know any textbook. It mixes up these number and space ideas, and then the proof becomes very complicated. It is pure mathematics is one case in point. That proof looks complicated and it's long. If you divide it into these two parts, space part and the number part, then the proof becomes natural and better appreciated. Now, about the major results about the real line. The real line is the space that is I am describing. So make it a topological space by declaring open intervals in the ordered sense as a basis of open neighborhoods of topology. So basic notions of general topology are compactness and connectedness. And the major theorems about the real line is that a closed interval is compact. And we actually have a classification of connected subsets of the real line. Namely, they are essentially infinite by infinite or one-sided infinite intervals. Now, there is another little topic, notion of arc connectedness. Now, how does this arise? We have to understand, we have some space and we want to understand this. Now, we feel that we understand the real line. Good. Then try to compare with the real line this space. So, what can we ask? For given 2 points, there should be a continuous map of a closed interval into the space. Such a map should exist. If such a map exists for any 2 points in the space, then the spaces are connected. Yeah, I think the other idea is the manifold. I don't want to go into this, but the manifold is the vast generalization of a non-singular real or complex algebraic variety. This is due to Riemann, who was motivated by far more general philosophical considerations of bringing in sets and structures on sets with legitimate, and these are legitimate mathematical objects. Riemann's paper on this is also very philosophical, where he introduces this idea of a manifold. His major motivation came from physics, and as usual, he went far beyond even his motivation. Then what we have wonderfully is more complete classification of connected Hausdorff 1- and 2-dimensional manifolds. So what Professor Ramdas was describing genus G surface. These are for every integer G, every natural number G, including 0, there is only one compact orientable surface of that genus. Complete classification. And I think even in our topology courses, we don't prove this theorem somehow. And this theorem has an interesting point that nobody claims credit for this theorem. Or nobody gives credit to somebody else that you prove this theorem. But proof is not trivial in any case. And okay. And now up to this, what I have talked about, I do not need real numbers. I do not need real numbers. Only on the original notion of the real line, one can develop all these ideas. Now, real numbers can be made, real line can be made into real numbers. There are various choices of that, where you use the point, call it 0, call it 1, 2, 3, 4, etc. So, in uncountable many ways, you can make the real line into real numbers. fix one such numbering, and let capital X be a function from the real line to real numbers, be the function that attaches to each point in Rn the corresponding number. This S is the coordinate. The polynomial expressions in X, coefficients in Rn also make good sense. And even rational functions make sense for taking away some finite number of points. And take complex numbers, complex line is RL square, is RL cross RL. An amazing fact, in complex numbers, you can add and multiply points.
नेटवर्क अच्छा है, वॉइस सही से आ रही है?
Yes, and so it becomes an extension field of the real numbers. Now, I want you to muse in how many ways can you make this complex line as an extension field of the real numbers. So, answer from the field theory, you know that any extension field of these of the type, one ring of polynomials in one variable with coefficients in real numbers divided by the irreducible monic polynomials over real numbers. Now, you have to use this deeper fact by the fundamental theorem of algebra. Such a polynomial is of the form x square plus ax plus b, where a square minus 4b is less than 0. This really acts as the geometry or arithmetic of real numbers. Arithmetic. Any such rule will give an algorithm to multiply points in CL. But now x square plus 1 is one of these polynomials, and square root of minus 1 is I, and that is our usual description of complex numbers. Unfortunately, all these, starting with other irreducible polynomials, you get isomorphic fields. So you can as well take the irreducible polynomial to be x square plus 1, and that's our usual introduction to complex numbers. And another important fact is complex numbers are algebraically closed. So every polynomial with complex coefficients of degree at least 1 has a root. And now this is really a topological theorem. Underlying general principle is really proper mapping between locally compact topological spaces. Proper means continuous and inverse image of compact is compact. And so polynomials are the only proper maps after you choose that one coordinate. And now a more general notion is the holomorphic function. And the topological properties of holomorphic functions are, there are, first of all derivatives exist, blah, 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 blah. And if the derivative is not 0, then there is on a certain neighborhood of that point, if you restrict the map to that neighborhood, it is a homeomorphism. And more importantly, this is the singularity case, where the derivative is 0, then there exists some unique natural number n, and a neighborhood of that point, such that after choosing the proper coordinates are at your disposal, the space is there, and the structure of complex numbers is there. So you can choose coordinates, so the map is z goes to z to the n. Z goes to z to the n. And in general, the 0 set of f prime is discrete. Okay, you know, there have been many results in the early part of the 20th century where there are some of these properties, many papers, even Morse wrote a book on such paper. And Stylov and these people, they they just consider the topological properties of holomorphic functions. Then you consider this spatial function. Z goes to e to the z. Now its derivative is never zero. So locally it is always a homeomorphism. But it's not surjective. It omits only zero. So it's a map from C to C minus zero. And it's a surjective local homeomorphism. And its usual periodic property, f of z plus 2 pi I is equal to fz, translates into topological property. Given a point q0 in C minus 0, and there exists a neighborhood V0 of q0, such that f inverse V0 is a union of disjoint open sets where I is varying over integers, and such that f, if you restrict to that one of those open subsets, then it's a homeomorphism. This is the difference between local homeomorphism and homeomorphism. And yeah, so, but this is a very special type of local homeomorphism. And this was generalized vastly by Poincaré at the end of the 19th century. And this notion is called a covering. And he related that to the fundamental group, which is the group of oriented loops and homotopy, etc. on the space. So this covering space theory, you don't need this base point and nothing. The covering space theory is just a view from the top to bottom. Whereas if you first, perhaps that you should be presented first in our lectures, top to bottom, without these base points and oriented loops, etc. And now, after learning this usual treatment, we can go from bottom to top. Okay. And there are some important things to say on this, but yeah. Now, I come back to the group theoretic background of this historical ramblings. Okay. It's actually a generality about completely general group actions, nothing special about these families. Let a group G act on a set X. And the point to think about, even if we learn group actions, but do not define the later spaces. See, for a human mind, it's easy to consider subsets of a set, but more difficult to consider quotient sets. If a group acts on a space, then each point has an orbit. Consider the quotient space where all those points in the orbit are identified to a single point. So this is the quotient space. And there is a natural projection map. I consider X as the space on which the group acts, and X mod G as this orbit space, the space of orbits. And this is a natural projection map. I'm just describing this complete generality. I'm not assuming anything about topological space. Now, if H is a subgroup of G, we have canonical maps of X onto X mod H. And the canonical map of G mod H. G mod H is not a group in general, but it's some homogeneous space, and it's a map from Y sub H to Y sub G. Just the orbit of H is contained in the orbit of G, and we just map the H orbit into a G orbit. The interesting thing is, if the two groups are conjugate, if there exists a G such that capital H2 is equal to G H G inverse, I think I should take it further. No? Then there is a canonical bijectory map of x mod h1 to x mod h2. Now you pick up the G in the definition of conjugacy. So multiplication by G is defined on X. And that map also defines a map on the quotient space. G mod, G bar, I call that map G bar of the orbit. This is equal to now G H1 G inverse Gx. And G H1 G inverse is H2. So if X is going to little gx on X, then in the quotient space, this H1 orbit of X goes to H2 orbit of Gx. It's a completely natural map. And in particular, if H is a normal subgroup, then it's a map of the quotient space on YH into itself. And then there is a normal subgroup. So G mod H is a subgroup, and G mod H is a covering transformation group of YH to YT. So let me tell you what is, how much time is that? 20 minutes. So I give you Abhyankar's idea of high school algebra. What does he mean by high school algebra? So one or more polynomial equations in one or several variables. In high school, we do only one variable anyway. But regard power series in one variable as infinite polynomials. And when we say dot, 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 that's really a mathematical expression. Dot, dot, dot. That means these terms are going to infinity. This is a different type of infinity. Then it's not a number, but it's a process. And in that thing, we can write down in some formal sense 1 plus x square plus dot, dot, dot is equal to 1 over 1 minus x. So manipulate using additions and multiplications, assuming field properties for coefficients. Now this x is a coordinate. You see, it's not intrinsic to the space. And that's why this 1 over 1 minus x and this power series has radius of convergence only absolute x less than 1 in complex numbers. But 1 over 1 minus x also makes sense outside this. And if we take some other point, then we can expand 1 over 1 minus x based on that point. And you get very different series, but it is the same function. And that was Riemann's deep understanding that what is happening here is an analytic continuation. Anyway, so with this understanding, now what is the problem of algebraic geometry according to Abhyankar? So I feel take m polynomials in n variables, put that equal to 0. The total degree of a monomial, a single term, is the sum of the degrees of each of these xi. And let the total degree of f sub I be d sub I, which is the maximum of the total degrees of the monomials in Fi. Then what does he mean by deformation of this system? Change the coefficients. Over real and complex numbers, you will change it little bit. Over general fields, you cannot say, just change them. Okay, and hope that still the many properties of this solution set carry over. Now, in the special case, when the total degree is 1, just these are linear polynomials. This is the problem of linear algebra. And the special interpretation is this, that consider x1, x2, xn as a point in the affine space, n-dimensional affine space. Then intuitively, this Fi equals 0 is a subvariety of dimension n-1 in the n-1 dimension, n-dimensional affine space. And you are in the linear algebra case, this is just a one co-dimensional subspace, n-1 dimensional affine subspace. And the solution set of star is the intersection of the n sub of the whole system. Is all n sub varieties of dimension n-1, and it's a subvariety of dimension n-n. Now, in the linear case, we will say that generically, what is happening? The number of equations is greater than the number of variables, then the subvariety is empty. It's true for n equals 1. You would say that I'm just saying, take a linear case. If m equals n, then there is a unique solution. If m is less than n, then the subvariety is higher dimension. And so this is the linear case, and Abhyankar recommends that assume that this holds also when total degrees are greater than or equal to 1. He says, have faith in God and march on. If you fail somewhere, still do not lose faith in God. Have confidence that something is true. You have to find it. And I say you will find it if you have a supporting family and a good source of income. But the interpretation of something is up to you. So what I say, I obtained something, is up to you. You decide something is up. But have a positive outlook. That much you have to say. So Abhyankar's view of, the main point is Abhyankar's view of mathematics is algorithmic. He calls it high school algebra. It does not mean it is accessible to high school students. Not at all. His high school algebra includes power series, Laurent series, even fractional exponents, and so on. But there is a certain difference between when he says algorithmic, it's not algorithmic in the sense of computer science. Abhyankar would, starting point is the base field. And you just want to consider that the base field is something known. So real numbers are known, complex numbers are known. So whatever the transcendental aspects of real numbers and complex numbers are there, they are not under Abhyankar's consideration. Now, here is a very good example that he gives in his paper. Now, you see, consider a polynomial of degree n. A0, A1x up to an x to the n. Then if you divide by x to the n, and A0 not equal to 0. If you divide by x to the n, you get a polynomial in 1 over x. And the A1 will be the coefficient of the degree 1 over x to the n minus 1. And you know that sum of the roots is equal to that first coefficient of the sine, I guess. And so if you use that formula, then the sum of the original polynomial effect, px, sum of the reciprocals of its roots is minus a1 by aj. This is true in the field theory, in any field theory. Now, a minus a1 by a0 makes sense on the ground field. Then the roots will exist in some extension field. And if you add those roots, their sum will be minus a1 by a0. Okay? Now, Abhyankar would say, don't end up at n, put dot, dot, dot. So that is the power series. Now, conjecture that takes is a power series that represents the entire function C to C over complex numbers, if P0 not equal to 0. Now, for making the conjecture, I have to say it's subjective. If it's not a subjective function, like Z of P to the Z, then that is, the result is not true. Then suppose the sum of the reciprocals of the roots he is taking, now that will become a series, and that sum may not be convergent. So assume that the sum is convergent also. So if that is true, then sum of the reciprocals of the zeros of that infinite power series is minus A1 by A0. So this is in some ways reasonable. Abhyankar says that this way Euler proved that if you put for x, for px cos root z, it doesn't make any comments. He says put cos root z, and he has its power series, you can write down, and then its zeros of cos, you know, is 1 over 2n plus 1 pi in integer. And so zeros of cos root z will be the squares of these numbers. And so you get a beautiful thing that if you take 1 over the sum of squares of the reciprocals, it's pi squared by 8. So the last result is proved in and can be proved by using other methods, more sophisticated methods with complete proof. But this is probably also, in a better way of thinking, this is a proof. Now, I would immediately say this argument does not apply to cos z itself, because you get the series summation 1 over 2n plus 1, doubly infinite series, which is divergent. But it is true in a way that, but it's a doubly infinite series. So you cancel 1 over 2n plus 1 with minus 1 over 2n plus 1, then the sum is 0. So if you do the cancellation, then the sum is 0. And the yeah. So, you know, you change square root of z by z to the 1 over n. And his philosophy would agree, and sometimes you will get something and you will get some possible results. But now the natural question, after we define functions in the seriously, the square root of z in the original case is not defined over complex numbers. It's defined over the double cover of complex numbers. Square nth root of z will be defined on the nth cover of complex numbers. So those are Riemann surfaces. Now, whenever Abhyankar uses the word geometry, he only seems to mean affine or projective geometry. And there is no metric or measure or even differential topological sense to this, let alone differential geometry. For there is no inverse function theorem in algebraic geometry. Have you thought about this? In algebraic geometry, they don't see here the inverse function there, and it doesn't exist.
There is Hensel's lemma.
Huh?
I think Hensel's lemma is usually regarded as the equivalent.
Does the inverse function theorem exist in the world of polynomials or?
No, so we have to work with performed functions.
Yeah. So you have to extend your idea of what a function means. But that is the reason why Tarski had to prove what is a non-singular point of a variety. It's not the same as usual point on a manifold. Because when you change the coordinates, you have to take the inverses, and those inverses don't exist in the world of polynomials. And so he has to formulate everything in terms of the locally defined power series and regular local ring and all that machinery. Its advantage is it makes sense over any field, not just over a real or complex numbers. There is no notion of orientability in his algebraic geometry. His standing crucial hypothesis is that the field is algebraically closed. And for complex numbers, it is algebraically closed. And there is everything is naturally oriented. So every complex projective algebraic variety or affine algebraic variety is orientable. So non-orientable manifolds don't exist here. A Mobius band doesn't exist. For him, Mobius band is not a manifold. A real projective plane is not a manifold. Yeah. So when Abhyankar calls a curve a solution of a polynomial in two variables, fxy equals 0 in C2, a complex curve. Now that curve is topologically a real two-dimensional orientable surface. And its singularities will be point singularities. This is a very crucial understanding. Now, if you consider the underlying topological space, complex line square, this curve is in two variables. So complex line square is real line to the fourth power. And the singularities of algebraic curves that he calls are possible self-intersections. But then the self-intersection is only one point. But if we take a surface, so in the usual picture of singularity is like a surface in R3, if it intersects itself, you will not get the intersection is not a point. Intersection will be curved. So these things are avoided in this picture. So he's already thinking in terms of RL to the fourth. There is no working for him in RL2. Now here is the crucial point. Now if you take a non-singular projective algebraic curve in the complex projective plane of degree D, then degree D is some algebraic invariant. And it has genus. This is a topological idea. D minus 1 to D minus 2 by 2. Now, this is a quadratic expression. So, for example, the non-singular projective algebraic curve of genus 4, you can write down the equations. But it can never be, even after deformation, you cannot make it non-singular. It will always have some intersections. It will always have similarities. So I believe that any projective algebraic curve defined by a homogeneous polynomial in three variables can be deformed by varying coefficients. Even by varying coefficients in the genus 4 case, you cannot avoid the singularity. But you can avoid the singularities when the singularities are of a special type, which they call ordinary double points. Ordinary double point. And I think in this resolution of singularities, if you come to this stage, you are already done. With more complicated singularities, you have to reduce to these ordinary double points. So locally, one may view an ordinary double point as two disks, two-dimensional disks, intersecting in just one point, which is a good picture in R3. So the correct picture is go to R4. So it may be guessed that an abstract compact Riemann surface, if it can be given algebraic structure, is always embeddable. Yeah, but it's not embeddable in two-dimensional complex projective space. But it may be embeddable in three-dimensional complex projective space. Because this point singularity by deformation These point singularities, if there are two arcs meeting in the plane, in arc 3, you can remove the intersection. The same idea in terms of equations, it works. And in P3C, it gives a reasonable conjecture that a compact Riemann, every compact Riemann surface can be embedded in three-dimensional complex predictive space. Any aspect of a Riemann surface. What about the algebraic structure? So algebraic structure is given by this branch coverings, and the inverse image of a point are finitely many points. So with these finitely many points, you can concoct some polynomial equations. So that would prove that the compact Riemann surface has a branch covering of the sphere, and then that means it's a holomorphic map into P2C. You can arrange that. But then Kodaira proved a serious theorem, even in n dimensions, that n-dimensional complex manifold with an integrality condition in the second cohomology group can be made into a projective algebraic variety. And it can be, projective algebraic variety can be embedded in 2n+1 dimensions. So for n equals 1, it gives you the number 3, and this is reasonable. So Kodaira was a field student for this work for n equals 1. This work. But for n equals 1, this gives an abstract one complex projective algebraic variety can be embedded in a non-singular way, avoiding all singularities in P3C. But now suppose this curve is sitting in P3C. Abhyankar's question, can I define by polynomial equations? Something one-dimensional object is a three-dimensional object. So one equation is not going to suffice. So there should be at least two equations. So that is the case in algebraic geometry. They call it complete intersection. So will that be always a complete intersection? Again, some problem. It's not always a complete intersection. So there will be at least three polynomial equations you need, and that's over the idea of the in the complex numbers. But this is one other direction in Abhyankar's work in which to do this over algebraically closed fields. And this was his continuing work with Mo. I think he did some 10 years work on this, how to write down equations for a curve in free space. Now, I proved a few things on this, comparing real and complete geometry. I used to send my papers to Abhyankar. He would never make any comments. Somehow he, I don't know why. Yeah. One of my papers was published in the Indian Journals. Good paper, I like it. But Abhyankar would not make any comment. Okay, now let me make some final remarks that this paper has a very large bibliography. It shows Abhyankar's historical scholarship. I think Abhyankar knew French, German, Italian well enough to read mathematics without any hindrance. But I found this rather interesting. On the first page, he recalls the origins of the subject in what he calls complex function theory, that means Riemann surface theory. And he mentions Abel, Jacobi, Riemann, Zariski, Picard, Poincaré, Lefschetz, Hodge, Kodaira, etc. Griffiths. These are the names he lists under on the first page. But curiously, in the bibliography, there are references only to Abel, Jacobi, Riemann, and finally, one modern mathematician, Griffiths. The other mathematicians, their work is not mentioned there. Not in the references. He mentions them as very good mathematicians who have proved results, but it doesn't mention any of the papers. Now, he used to mention his frustration with Grothendieck on several occasions. In historical ramblings, in this paper, it comes up in read section 37 and 38. And many people who are studying the subject around that period, 1960 to 1970, will agree with him. What he said, he had a point. I know, for instance, C.P. Ramanujan of TIFR was one of them, was very critical of Grothendieck's style. But now there have been many expository papers and monographs, so the subject has become more tractable. And this paper contains a lot of unusual insights of Abhyankar because he wanted to generalize all these to characteristic P. So many crucial arguments there. And so that was his real work. So I request Faculty to organize a week of people like Gorpade, Ramanand, Kapil Paranjpe to explain some of the sections of this paper to all students. That would be a great service and it will be better than these types of just 1 hour lectures. Thank you.
Let's thank the speaker.
Those are online if they want to ask any questions. Oh.
Are there any questions? Online participants, please. Let us thank the speaker again. Thank you, sir. Thank you.
I thank the speaker, Professor Ravi Kulkarni, and also I thank the chairman of the session, Professor Vinay Joshi from Abhyankar University. Now we have 5 minutes break and then immediately start the next talk. Yes, thank you. So we have this 5 minutes break.
Can I make a small comment? Hello?
Yes. Hello, please. Yes.
No, it's always interesting to hear Professor Kulkarni. He has a special perspective on things. Just one very, very minor thing. You kept saying Purdue University at Indianapolis. I don't know why. I mean, but, you know, the one at Indianapolis is or used to be at least the common Purdue and Indiana. Purdue University was always, I think, at West Lafayette.
Lafayette.
And not Indianapolis, right?
By car, I used to drive to Indianapolis and then go to Lafayette. That's right. And Indianapolis was a major city. Lafayette was a city nearby. No, I should correct it. Lafayette.
Okay, and also because Gorpade is here, I think he should pick up this explanation of the historical branding. Thank you.
I didn't hear your last remark, Professor Karthik.
Hello, I just was saying that Professor Ravi Kulkarni, who talked today on this historical rambling in algebraic geometry paper of Professor Abhyankar. So he has suggested we to explore more on this paper, and there are various.
It's a great paper, of course.
Yeah. So various sections one should explore more by organizing some 1 week workshop on this paper itself, by inviting more people have expertise in this.
Inshallah.
Yes. That's a suggestion.
God willing.
Thank you. So just 5 minutes break, slightly late, but 5 minutes break and then we will start. Yes.
So, you know, this paper will be referred 20 times more in next 20 years.
That's true. I mean, and
understanding. Yes.
So, you know that the original version of the paper had some stronger remarks on Grothendieck and so on. And but Abhyankar had to tone down some of them, possibly at the request of editors of American Math Monthly. But also he was very keen that it should appear in Monthly, because the kind of readership Monthly has, no other research journal have. So there were things which were kind of like appendix to the paper, and they were published elsewhere. I mean, you must have seen there is a famous poem of Abhyankar, Polynomials and Power Series. And it's sort of, you know, this had its origin in some history conference. But then, you know, I think it was a good thing that the paper was published in Monthly. You know that it won the, I think the Ford Prize, which is for best paper, expository paper in the year, and then Chaunet Prize for best expository papers in the whatever preceding 4 years, etc. And it is certainly, you know, very widely read and so on.
So Sudhir, yeah, let me ask some question to Sudhir.
Yeah.
What I said, a combination of these non-singular.
Sorry.
Is my original explanation correct? This field is transcendent.
I'm sorry, your voice is breaking. I'm not able to hear contiguously.
I interpreted the desingularization project as with a field of start with the field little k and constructed transcendental extension of degree n with some extra algebraic algebraic elements, so finitely generated over little k. So the effort was to create a non-singular projective algebraic model for this. But so that the order function field will be k.
Yeah, but it's actually, you know, it's sort of a little more than that. So yeah, in the curve case, it is.
In the curve case, it's complete, but now for n equals 2 case, P1 cross P1 and P2 are two models of just a transcendence, a pure transcendental extension.
Correct.
So the risk you are studying some minimal models in that case.
Yeah, that is true, but
did Abhyankar work on any minimal model problems?
Not exactly. Actually, the minimal model is more popular for three-folds and so on. But the sort of typically what happens is, you know, you want to show that a given variety is birationally equivalent to non-singular algebraic variety by a by sequence of these so-called monoidal transformations. Right. So that's sort of always built into these things. And what sort of Zariski had shown is that, you know, you could prove this so-called local uniformization, which is somewhat technical. You know, then the problem is sort of reduced to doing that, which is what he did for surfaces in his thesis. And about 10 years later, he did it for varieties of dimension 3, you know, in characteristic P, say greater than 5.
Okay, I think you come to Pune sometime. We should discuss.
Yeah, but you know, I mean, I think today better expert on resolution is Del Katkowski. He's sort of a postdoc of Abhyankar. He has lectured in this series before, and he's also written a nice monograph on resolution of singularity as well as an introductory book on algebraic geometry. Most likely, Dale will be visiting India around the end of this year or so, and maybe next year also. So, if somebody is genuinely interested in resolution, not really the right person to talk about it, but Dale can certainly, teach us something.
You can suggest some people, maybe.
Yeah.
Maybe 10 people of us will come together. Please arrange that when I am here also.
Okay.
Thank you.
Okay, so thank you, Professor Kulkarni and Professor Ghorpade. And now we shall have the next session. And I see that actually Professor Bhatodekar has to go to his house, and probably he will join online only. Let us see. And maybe, yes. Yes. And see. So now there will be talk by Professor Lenin who is from US. Actually, right now he is in Germany. And for this talk, Professor Meena Gupta will be in chair. And I see Professor Abhyankar also here. So now I request Professor Meena Gupta to unmute herself and share the session. Possible?
Good evening,
so video also. Please start your video also.
Hi, Neela.
Hello. Hello, sir. How are you?
I'm fine. Thank you.
Thank you. Nice meeting you after a long time.
Yeah.
So we welcome Professor Makalyamanov on this occasion of 193rd birthday of Professor Shreeram S. Abhyankar. We have, from the morning, this lecture series has been going on, and we have heard so much about him. Now, it's my pleasure and an honor for me to introduce Professor Makalyamanov on his birthday to give this talk. Professor Makalyamanov, you all know that he has been working in the area of affine algebraic geometry and associative rings and non-commutative as well as commutative associative rings for more than 45 years, if I'm right. He was also honored with the inaugural fellow of American Mathematical Society for his work. I am specially indebted to him for his work on, or his discovery on the results of Makalyamanov invariant, which we all know, and his impact and its impact on the affine algebraic geometry. This has helped the people in affine algebraic geometry to give a simplified proof of many well-known results, and proof of which would have been highly complicated and difficult without this breakthrough. To name a few, the first one I know is of the an easy and simple proof of the cancellation theorem of Miyanishi's cancellation proof for dimension 2. That is probably the only proof I know because of him. And the other proof is this Abhyankar-Mohs epimorphism theorem, famous. That also can be given using his invariant, and it also has helped to solve many open problems, namely the discovery of this proof that this chorus SL threefold is not an affine threefold, which led to the solution of the linearization problem for the C star actions on C3 is linearizable. And even my own work on the Zariskis cancellation problem in positive characteristic is because of his techniques, which I could understand and apply. It's an honor for us that you have accepted this invitation. I welcome you, sir, very much. Thank you.
Okay, great. Thank you for introduction and regards from Bonn, where I am now in Max Planck Institute. And I think I need your permission to share the screen.
I think you can share. Somebody from the
I can do it.
Organizing committee, can they allow me to share the screen?
Can you see my screen now? Conjecture on the algebras? Yes, no?
No, sir. Let me.
Okay, let me. Okay, I'm unfortunately not extremely versed in all this. I hope that.
Same is the story everywhere.
Okay, and unfortunately today is Saturday and technician is not here. So
there is some share screen. Share screen. Green arrow is there.
Okay, so let me try again.
Green arrow. Please click on that.
That is bizarre. Okay, so let me. I thought that I can share any of the screens which I
want. So you share the screen which you really want to share with us.
Okay, but when I'm here, that's what I want to share, but you don't see it, I'm afraid. Do you see a conjecture algebras?
Below you have share screen button below. Below you see now on the screen below. Share screen is there in the center.
Okay, well.
Oh, we are probably able to see your screen.
Can you see my screen now or not?
Yes.
Yeah, but when I'm calling.
The Wayne State University screen.
When I'm calling for. Okay.
There is
from
email below and black box above it.
Okay. Well, let me maybe kill this. Okay, let me. Okay, so here I'm pushing you share. And I cannot. Yeah, I'm sorry that. Okay. Maybe this would be. Okay. I have a full screen now.
But it's a black screen.
Yeah, you just see a black screen. Yeah, nothing else. Yeah. Okay. Well, that's unfortunate. Let me try to. Okay. Now I'm completely confused because I don't see anything.
It's a board, black board.
Okay, let me stop share.
Yes, it was coming.
Okay, so how can I? How can I share a particular screen? Okay, you know what? Let me try to kill everything which I can kill, and then maybe then it would work.
You have to share the screen again.
Okay. Let me kill this one. Okay. And now let me try sharing again. Yeah, somehow I don't see, I see this is the
Yes,
see this. Okay, advanced content, computer audio. Well, yeah, that's really awful. Well, look, I cannot see, I cannot show you screen. I can read it out loud, but it's probably not what we want to have, right?
You did it earlier. So what you can do is that you can close every other window. Just keep only the window which you want to share.
Okay, so okay, so suggest that I will really everything with exception of this window. Let me try this.
Yes. And just keep open only those slides which you want to show.
Yeah, okay. Let me try this. Okay. Okay, that's what I want. Let me kill this as well.
Now you can just click on share screen.
Basically, what I want to do is to share with you some attractive problem, which, okay. So let's try now. Share screen. Fortunately, it shows me something which I even don't have now. It shows me posted and Zoom. I don't understand.
You have to open the PDF file which you want to share.
I'm sorry, once again.
You need to open the file which you want to share.
Okay, it's open now.
Now you click on share screen.
Let me share. Okay, You're saying that now I have to share again, and then we'll
click on share screen.
No, I still don't. I see desktop with Nina. I see another desktop with Nina as well.
So below you see there is a green button with an upward arrow.
Green button. Is it the green button which is called share?
Yes.
Okay. I'm pushing it, but I don't see the screen which I want. And actually, what I do see, I see screens which I try to kill. Actually, let me. Okay, maybe I didn't kill everything.
Yes. Now yes, it is available. Yes.
So you see, probably it's very difficult to deal with a person who is this. Who is, you know what? I think I even managed to kill the screen which I wanted. Okay, no, it is here. Okay, the algebra. Okay. No. Okay. So let me try one more thing and then, then I'm afraid I have to give up.
You can do one thing. You can share your screen with me, and you can send the PDF to me, and I can share it.
Okay, let me try to do this. Okay, but now I am. Okay, so let me. In my enthusiasm, I kill everything. So now let me try to find this document again. Lenny, floppy, talks. Now a conjecture on the algebras. Open with ocular. Okay, so I opened it now. That's the only screen which I have now. So let us try sharing, right? Okay, great. Can you see it now?
Yes,
we can see your screen.
Wonderful, I'm so happy. Okay, so first of all, let me start that, I met Professor Abhyankar quite some time ago, not that I can recall it, and I can agree with the previous speaker that Ram's vision of mathematics was very unusual and very interesting. And if you try to read his paper, his and more paper, high school theorem, you will see a lot of things which is hard to understand why they're there. And I think Avinash explained to me that he had some notion of equilibrium, and that's what it is. But anyway, so I certainly cannot share as many interesting insights in his life as the previous speaker because I didn't know him so well. I know him sort of by name in Russia in early 1970s, but I came to the States much later and I met him not immediately. Anyway, so what I want is to talk about topics which were of interest to Ram, and it's his interest in Jacobian conjecture, and that's basically why we were interacting with him, because I'm interested in this conjecture for many years. And as you probably know, that there was the longest surviving proof of Jacobian conjecture by Wolfgang Engel. It was published in 1955. And until 1970, it was a proof. And then simultaneously, apparently, this I don't quite know, but maybe Sudhir can help me here. I think that Abhyankar began in about 1970, understood that there is no proof there. And in Russia, Vitushkin and with my assistants start working on this paper of Engel, and we discovered that it is wrong. And then Vitushkin actually published something in his talk in 1973, which was published in 1975, and then it became officially, again, an open question for dimension 2. That's what I forgot to mention. Now, this last year was somewhat unusual because in this year, two proofs were published, dimensional case. One in Archives of Mathematics by a German mathematician, Wolfgang Bartenwerfer, and another was published in Journal on Differential Equations in Russia by Belarusian mathematician, if I remember correctly, Vladimir Amelkin. Unfortunately, both proofs were wrong, but it took me quite some time for interacting with authors to actually force them to admit their mistakes. So as usual, the problem is slippery and it's still open. And I still strongly recommend to young people who don't have tenure not to work on this problem, because I know several mathematical biographies which were actually completely, smashed by these attempts. And usually there are several proofs on archive, and right now there are some proofs, but I don't read them because otherwise I won't have time for anything else. So now to the topic of my talk. So what I'm going to talk about, some object which I want to popularize, which I named D-algebras, they're somewhat similar to D-modules, and some conjecture about these D-algebras, which, if proved, will immediately imply Jacobian conjecture. So here is what is going on here. So consider a polynomial ring in n variables and an algebraic function given by, say, a reduced polynomial p of n plus 1 variable. And y would be algebraic function of variables x1 and so on xn. If we consider field of fractions of this, so what we have to do? We have to take a ring in n plus 1 variables, factor out by ideal generated by this polynomial, then consider field of fractions of this algebra. Now, if you look at partial derivatives of your algebraic function y, partial derivatives on a ring can be extended to this field, and we can compute partial derivatives of our algebraic function y. And algebra, which I'm interested in, this T algebra of y, is subalgebra of f, which is generated by all n variables algebraic function y and all its derivatives. So if you prefer this language, it's a left module over nth while algebra. By algebra to algebraic function, you this the algebra. So this is kind of a D module as well. Now, here is the conjecture. We have the following interesting dichotomy. If y is a polynomial, actually, yeah, so the simplest case, then whatever you do, you take partial derivatives, you are not getting anything new. So this algebra will be just Cn. So conjecture is that if y is not a polynomial, then resulting algebra dy cannot be embedded into polynomial algebra. Of course, if it can be embedded, it will be polynomial algebra with n generators, because the transcendence degree of this algebra is n. Okay, so that's kind of a rather wild conjecture. Well, actually brave to call it conjecture, though there is a wonderful word which one of my Polish friends taught me is suspecture. When you suspect that something is true, but don't want to actually conjecture it. So Jacobian conjecture, again, I remind it, I'm sure all of us know it. Okay, it was formulated by Keller in 1939. And it follows immediately. From this conjecture, I explain, of course, how it is. So suppose I have n polynomials with Jacobian equal to 1. Then I can describe partial derivatives relative to these polynomials. Of course, I don't know that they are generators in this algebra, and that's what actually we want to prove. But nevertheless, partial derivatives relative to these polynomials can be extended on this whole ring. And the formula is quite simple. If I want partial derivative relative, say, to Fn, then I take just Jacobian. In this example, I'm taking partial derivative of x1 relative to Fn. So you just replace one position by x1, and then you're getting corresponding partial derivative. Okay, so we can, in this way, define all partial derivatives of this algebraic function y. So suppose we have a counterexample to Jacobian conjecture, namely that subring generated by this n-tuple is not all ring. Then, of course, I can assume that one of the generators, xi, is not in this ring. And for the sake of argument, I can say that x1 is not there. And then I can define all partial derivatives in this vein. And if conjecture about the algebra is correct, then we immediately get a contradiction, because in this situation, when I'm computing this Jacobian, it's still a polynomial in original variables x1 and so on xn. And so it is embeddable in polynomial algebra. If conjecture is correct, we'll have a contradiction. Well, so I have some kind of a problem, because on one hand, I want to believe in this conjecture. On the other hand, I'm not sure that Jacobian conjecture is correct for any dimension. I'm kind of positive that it's correct for dimension 2, but I'm not so sure about higher dimensions. So one of my friends pointed out that I have some cognitive dissonance here, but well, what can I say? So what I want to do now, I will prove it in several cases. And so that will sort of explains why I think this is true. Unfortunately, even in the simplest case, when I have just algebraic function of one variable, the proof which I have is not very nice in the following sense. It's very simple, but it's not something which can be generalized for a larger number of variables. So suppose I have this situation, I have algebraic function of one variable x, and assume that it's embeddable in a polynomial ring. Well, then I can think that it's embeddable in polynomial ring with generator t. And then, of course, x would be some polynomial of t and y will be some polynomial of t. Now, then there is just very elementary formula from calculus, allows us to compute partial derivative of y over the x. Yeah, so if f is function in c of t, then partial, then derivative, it's not partial. Here is just derivative of this, as we know, is given by ratio of derivatives relative to t. And so what will happen if y is f of t? I start taking derivatives. On every step, drop, I will have drop of degrees by degree of x. So by subtracting some positive number from a positive number, I either come to negative number, so I will not have a polynomial as a result of it, because polynomial must have positive degree, or result will be just 0. And then, of course, it means that f is a polynomial in x. So that's really trivial observation, but unfortunately, considerations with degrees do not work well when dimension is more than 1 and you're not in projective but in affine situation, because degree is very convenient notion, but it is not really very sensible, because actually notions which are sensible should be invariant under automorphisms. And needless to say, only when you take automorphisms of polynomial ring of one variable, degree stays stable. If you take polynomials in two variables, then automorphisms completely destroy your degree. And here is some simple example when actually degree standard, if you take just standard degree, will increase when you take derivative instead of dropping it as in previous case. Okay, so that's unfortunate, but that's what I have. Now, what would be very interesting is to have some robust impediment in this, even in this situation. So, for example, we would know that this algebra is not embeddable in polynomial ring if we will be able to prove that it has a non-trivial unit which is not a complex number. If this would be proved, then there is a hope to generalize it to higher dimensions. But I failed to do it, though in all examples which I was able to compute for this situation, it was always the case. I was always able to find a non-trivial unit. Okay. Now, another consideration is that for majority of algebraic functions, it is trivially the case that indeed algebra generated by y, this D algebra of y, contains a non-trivial unit. And again, it's very simple observation, which I present to you. So if you take a typical function, it doesn't have singular points. Singular points on this algebraic language means that the system of equations, polynomial itself is 0, and all partial derivatives of this polynomial are zeros, have a common point. So this 0 should be mutual for function to have a singular point. So typical function does not have a singular point. So if this is the case, then we know, and this is actually non-trivial theorem, that if this vector contain a vector of this polynomial and this polynomial and so on, this n+1 polynomials, if they don't have a common zero, then the ideal generated by these polynomials actually includes 1. It's a nice theorem. It's not trivial, but we can use it. So we will have this equality. And then if we just consider, summation of P over Py, so this is derivative, one of the derivatives, and these are also, so what is a partial derivative by X? It is, if you write it, it will be partial derivative. I'm sorry, there is a question? I cannot hear you, unfortunately. Okay. So what is partial derivative of y relative to x1, say? You have to take, as you know, as in calculus, and implicit derivation, and what you will see is minus partial of polynomial relative to x1 divided by partial polynomial relative to y. So this I can take because in our situation, it is just 0. This will be these partial derivatives. I put minus sign to take this here, and then I add I, and the result will be 1 over partial derivative of y, which of course is non-trivial unit, because it's trivial unit if only partial by y is constant, which means that y was a polynomial in these variables. So in this case, algebra is very easy to describe. So for a typical situation, that's what you have. So when you have singularities, you cannot immediately prove it, unfortunately, and so this is open question. Of course, now we can reformulate conjecture, and that may be the right way to formulate it, namely that algebra generated, this D algebra generated by y, always contain a non-singular, a regular algebraic function. Okay, so as we can see from this example, our problem is that we have singularities. So my next example is rational function. When I do have singularities, when I have a denominator. And in this case, again, it is not very difficult to prove that this algebra would be just generated by all x's and denominator, of course, with assumption that P and Q are relatively prime polynomials. Okay, so here is some proof. I'm not sure that we really need to follow it, but let me sort of outline it. It's proof by induction, and of course, base of induction is obvious. If n is equal to 1, then A and B are relatively prime polynomials, and relatively prime in strong sense. Not as not having factor, but in a sense that ideal generated by them contains 1. So you even don't need anything to have this unit. So this is a base of induction. And then because of that, when we're dealing with n-dimensional case, we can immediately assume by induction that this algebra contains polynomial in xy divided by q. This just because by induction we have to work over field of rational functions, and so because of that, you cannot assume that this is 1, but something which is invertible there. And in this case, it would be just polynomial in one variable. So we have a lot of fractions like this, and somehow I want to squeeze out of it actually that 1 over q belongs to this ideal. So you're looking at the ideals which are generated, ideals of elements with denominator Q in power I, and so you start looking at them, and then, I'm not sure that it's so interesting to look at it. You start working with them, you are proving something that are included and whatnot, and then that this ideal is containing one, and so you prove that it is just the case that in this situation you indeed have a non-trivial unit, which is 1 over Q. So again, it's not hard to prove, and of course, if any of you is interested in greater details, I'll be happy to supply you with preprint where all this is contained. And just write to me. My email is lml@wayne.edu. Some of you know it, and I will be happy to do it. Now, there are some consequences of this theorem. People who work with who are interested in Jacobian conjecture know that in some cases it is proved. It is proved, for example, if you assume additionally that extension over the field of rational field generated by all x's, if this extension of a field generated by all x's over a field generated by all f is Galois, or it's enough to assume that it is splitting field, which basically is the same, then actually these two fields are the same. And if these two fields are the same, then it's easy to show, and that's Keller did in his paper, then actually just subring generated by these polynomials is whole polynomial ring. So why it is, and this was proved by many people. The Galois case, there are different proofs. Some of them have slight flaws, but it is well-known fact. And it is not difficult to deduce it from this fact about polynomials, which I mentioned. And because indeed what you can do, you can, if you see the algebra generated by Y over the algebra will contain all roots of the polynomials. So because of that, it will contain all coefficients of this polynomial P, whatever, this polynomial, if we make it monic, in the first variable. So here somehow my Y became X. Again, it's just illustration how to bring it to contradiction for Jacobian situation. That's why Y is X. Anyway, what is easy to show that if X is this algebraic function, which does not belong to it, then if you take sufficiently many derivations, not important partial derivatives relative to what? We're assuming that it's not polynomial, so you're not getting stopped by 0 when you cannot progress. So that if you take sufficiently many of them, then monic polynomial for a corresponding derivative has rational coefficients. And if the situation is Galois, then these rational coefficients, as their symmetric functions of roots which belong to our algebra, belong to algebra. And then by previous statement about this theorem that if you have rational function, then the algebra actually contains Q in power -1, shows that it's impossible. And that's probably the simplest proof I know for splitting field situation. Okay, so what would be nevertheless interesting is to understand really well, not on the level of the proof which I suggested, how to deal with what are algebras even in one variable case. So not just to prove that this algebra cannot be embedded in polynomial ring, but real description of this algebra. And this seems to be non-trivial, but probably doable question. So what I started when I was experimenting is it was with trilinear functions. Well, I call them cubic algebraic function. What I have in mind that they're given by polynomial expression like this, and they're not really cubic algebraic functions because I'm not assuming that these polynomials have small degrees. They have arbitrary degree. Then you can start with playing with derivatives, and let me give you a couple of examples. I don't remember, couple or at least one, whatever. So say you have this example, you have this algebraic function. It has singularity, one singularity in 0.00. So I cannot apply this general consideration. But if I take derivative of it, then it can be written in this form. It's just, again, simple-minded computation. Okay. So then if I clear in this expression, just leave in denominator only x, multiply by 27x minus 4, of course, you can recognize this expression, yeah, discriminant of cubic polynomial. Then you will get that this expression belongs to your algebra. Now, if you multiply it by y, then y cube is divisible by x. Y cube divided by x belongs to the algebra. So this expression belonging to algebra tells you that y squared over x belongs to the algebra. But if y squared over x belongs to the algebra, then y over x belongs to the algebra. So we have this function in our algebra. Writing equation for this algebra, you can immediately check that this is non-singular function. And so we have a non-trivial unit in our algebra. Here is a more complicated example. So it's not all this simple. Here again, you have to compute derivative to see what is going on, but unfortunately it doesn't work immediately and it's more complicated. So you can compute second derivative. Well, it's boring but simple computations, and people who are more advanced with computers can certainly do it with computers. And then again, you start looking at what you have. And finally, you can show that indeed, with more effort, that y over x is in this ring, and then show that again you have a regular function, that this is a regular function. Similarly, you can play with this example, yeah, where you have just one singular point and figure out the same story. So you have regular function, you have a non-trivial unit. Now, here are a couple of examples, which I want actually to finish my talk maybe a little bit prematurely, which are related to Jacobian conjecture. Is one of the approaches with Jacobian conjecture, you're getting expressions which are polynomials in y, but are fractional, contain fractional powers of x, such that their Jacobians are constants. So here is one of the examples of this kind. And if not for existence of expressions like this, Jacobian conjecture would be very simply proved algebraically, but unfortunately, or fortunately, they exist. So this approach does not work. So you can easily check that if you take the expressions like this, their Jacobian will be -½ And now what can be said? It's clear that if you consider algebra, which is generated by f and g, and perceive x as algebra function of these two variables, all what you get by partial derivatives and what derivative relative to g would be Jacobian of f and x. So if you start polynomials y. So the only get into a unit is to have x in negative d, and which, and so if you take by taking, and then if you proceed with taking Jacobians with it, and of course in your algebra it is closed under Jacobian, you will get negative degree of x. It is not clear though that it is always true, and that will be really bad news for me, that in one variable case it is always a unit. Here it's a two variable case, and here we have a unit, but I'm not so in this more complicated have a unit. I see compute me show you this example. Again, if you take these two expressions, then you can straightforward computations show Jacobian would be a constant if coefficients satisfy some equations, can be expressed through C, and then coefficients of F should satisfy a couple of equations which can be solved. Try to rewrite this expression by introducing new variables, x in power 1 over 20 and v, which is x in power 19 over 20 y. Jacobian of these two variables is a constant, so you can use them instead. And in this way, you can rewrite your expressions now as polynomials in V and Laurent polynomials in U. And then if you start taking derivatives, you will observe that the leading forms of these derivatives. So this is expression for partial derivative x here will become u in power 20. Partial derivatives are having leading terms like this, and then there is some very subtle consideration related to ratios of these expressions, which shows that it cannot be embedded in polynomial ring. But this is really a very delicate consideration, which I don't have any hope of generalizing. On the other hand, I don't see how it's possible to prove that negative power, in this case, negative power of u will be here. Say, if I replace u in power 20 by u in power 10, it is true. But for this large power, I cannot do it. And of course, instead of u in power 20, I can write u in power 2000, and then I'm completely lost. So that was what I wanted to say. I want to attract your attention to this conjecture about the algebras. Maybe one of you will be able to build a counterexample or progress in it. And so what I think is doable and maybe reasonable thing to do is try to describe completely what are the algebras in the situation when you have just one variable case. So that's about it. That's what I wanted to tell you. And I thank you for being the audience. That's it. Okay. Any questions?
Thank you, sir, for this wonderful talk. And very difficult calculations.
There were some chats. Maybe there were questions in chats.
So, yeah.
No.
I have a question.
Yeah, go ahead.
So why are you considering that D of A that you have defined, that algebra, should be containing polynomial ring of one variable? I mean,
once again, well, can you repeat the question and being a little bit more loud?
yes, what I'm saying that why are you considering the DA that algebra, what we are considering, that should be embedded in the polynomial ring over one single variable. Why it's not?
Yeah, okay. It's not very difficult to show that if a ring with transcendence degree 1 is embedded in polynomial ring in n variables, then actually it can be embedded in polynomial ring in one variable. It is not hard lemma to prove. You can do it by sort of specializing your original n variables. You always can find specializing, sort of replacing xn by some a cleverly chosen complex number, and then it will become a polynomial ring in n-1 variable, which still contains an image of your original algebra. So in this sense, it doesn't really matter. Yeah, if you will be able to embed it in polynomial ring in many variables, in this case, it is the same. So you can just forget about this additional condition. It's not really important.
Thank you. Hi, can I ask a question?
Certainly.
Yeah, hi Lenny, this is Sudhir.
Yeah, I see it on the screen, yeah.
Yeah, okay. So is there a special reason why you think Jacobian is not true for n greater than 2?
No.
I mean, this is the first time. Yeah.
No, there is no special reason for that. But, you know, this is say if you take as example cancellation conjecture.
Yeah.
Okay, then in small dimensions, it's correct, but then it becomes not quite correct. You know,
correct.
Again,
Our chairman knows about that.
So generally, and yeah, I don't know.
No, but still we don't have any example in characteristic 0.
Yeah, so I don't know.
It's very much a characteristic 0 problem.
That is true.
Yeah, so it happens. There is no real reason for that. It's just kind of general. But as again, I said that I certainly have a cognitive problem here because I want to believe that my conjecture is correct for any dimension, and I don't believe the Jacobian conjecture. So there is certainly contradiction in my mind.
Well, these two statements are contradictory, right? Because your conjecture implies the Jacobian
they're certainly contradictory, right?
Yeah,
if this conjecture of mine is correct in any dimension, then Jacobian is correct in any dimension.
Yeah.
So you know, but you know, being an old guy, I permit myself to have inner contradictions.
You know what Severi used to say? That every good theorem has a good counterexample.
Yeah, well, there is a famous story about...
That was in different sense, of course, but...
Yeah, you know, Rudin, who was famous analyst, he once told to one of his co-authors, we should prove this theorem immediately before Alexandrov built a counterexample to it. And he meant Alexander Danilovich Alexandrov, some great geometer.
I see.
But that's
okay, I didn't know that.
Yeah, known story. Yeah.
Okay.
Yeah.
Thank you.
Sure.
Thank you for your lecture.
Yeah, I hope that it will, yeah. And I will be very happy to communicate about any progress in this problem. And again, I will be happy to talk about it and whatever, to collaborate.
Sure.
Okay.
Okay. Thanks.
So who is in charge now?
Yeah. So it's a very nice talk.
Thank
as
you,
we
Nina.
have said in the beginning that beginners should not work on this. So I don't read too much about this problem.
Yeah.
And only thing I had a few talk with Professor Asanuma. He claiming that there is an affirmative result for n equal to 2 using some topological, but probably he's just checking. This problem being so I should say notorious that even if we have a correct proof, we would be restraining ourselves to tell it publicly.
Yeah.
Now, after him, there are very few people who can actually check whether the proof is correct, or it's basically identifying the gap. Or,
yeah.
So that requires a bit of a real experts who can get into it and understand the difficulty of the problem and where it may actually lead to a problem. So, thanks for this talk.
You're welcome.
So let us thank the speaker again. A very nice talk to the topics of interest of Professor Abhyankar. So, in fact, Professor Mukar Himano had visited India on the occasion of the 80th birthday conference for Professor Abhyankar, which was organized in the University of Pune in 2010. So, we are very happy to see him again on this occasion of this lecture. And we hope that he comes to India again sometime. Yes, and I also thank Professor Meena Gupta for agreeing to be here for this session. Thank you very much. So Meena Gupta had also earlier visited Bhaskaracharyya Pratishthan and the University of Pune and has given lectures. So we invite you also again. And in the audience, I see many people who are close to Bhaskaracharyya Pratishthan. And I see Mahesh Nerulkar is here. Nibal Rama, Professor Ghorpade. In fact, Professor Ghorpade, he has a flight, but probably is delayed. That's why he is here. He has been here for a long time, which he said that he may not be able to be there at the end, but he is there. So he's always helping in the organization of this symposium every year, which you have been organizing for the last few years. So I thank Professor Ghorpade also. And I thank all the people who joined to attend these online lectures. Yes. So Professor Amartya Datta also, he came recently to the Bhaskaracharyya Pratishthan and gave many lectures on ancient Indian mathematics and his research regarding it. Yes. So I thank all of you, all the participants, all the speakers, chairpersons, and I declare that this symposium is now over. Thank you very much. Yes.